So, last lesson, we reviewed quadratics and cubics, and I promised that we'd actually get onto something new for 415, and we'll do so now. So, the last thing we looked at was cubics, and on the screen there was the last uh, thing we looked at, I suppose, which is when you've got a graph, what do you do about getting an equation kind of thing, and that there were different kinds of cubic functions based upon uh, the idea of a single a single factor, a double factor like x minus 2 all squared, or if you like, in a way, it's not a factor, but if you've got a cubed expression, then you're going to get a wiggle instead. Okay, so let's look at higher order polynomials. I'm going to show you some examples. I might actually have to sit up the front and do this, I think. Show you some examples in Desmos, but this is kind of what we're looking at here, that with the higher order polynomials, so remember, a polynomial function is one which has positive whole number powers of x. You can't have x to the half, you can't have x to the negative 2. So my understanding is that they could very well ask you to either graph a function or to take a function that you're given and produce the function. Sorry, take a graph that you're given and produce the function of powers higher than 3, but those polynomial functions will be able to be fully factorized, if you like. So you should be able to get it into factor form. What technique would you use to put it into factor form if it wasn't already? A combination of tools that you should have. You should be able to answer just like that, 415 students. Just like that. I have a polynomial expression and I need to get it into factor form. First of all, I would start with, beg your pardon? You know what, I wasn't thinking that, but that's an excellent answer because you should always do that first. Any common factor should be taken out first. Secondly, ouch, use the factor theorem to find another factor. Thirdly, use polynomial division to continue the factorization process. Okay, this needs to be like a no-brainer for you. It's recall. I'm not saying that you know how to do that, although common factor you should. Factor theorem you should. Polynomial division's a bit tricky, but with practice you'll get there. I'm not saying that you will always get it right, but what should be tripping off your tongue right now are those steps. Common factor, and then factor theorem, and then factorization to complete. Once it's in factor form, then you're GTG really, because each of the factors becomes a 0, and then it's what kind of 0 is it? So if it's a single linear factor, again, I'm just trying to cut down on how much theory you have to write. I'm so sorry about my voice. So if it's a single linear factor, it cuts through. So a linear factor means that it's x to the power of 1. So x minus 2 or 2x plus 1, something like that is a linear factor. So if it's a single linear factor, it cuts through. Excuse me, once factored. This is going to be a great video, isn't it? Just me talking for 5 seconds and then 10 minutes of me clearing my throat. Lovely, isn't it? If we're lucky, it might just pass an SMR barrier or something like that. But apart from that, it's pretty dodgy. Okay, if it's a squared factor, so like x plus 1 times x plus 1, or it's a linear factor that's squared. To be precise with my language, it's a linear factor that's squared. So x minus 2 all squared or 3x plus 1 all squared. Then what does it do? Someone shout it out. Yep. I'm going to use a slightly different language, but saying touches is absolutely right. I tend to use the word bounces because that's kind of what it feels like it does. Boing. Bounces up or bounces down. And if it's a cubic factor, a cubic linear factor, What's it going to do? Hamish? Yep, that's an excellent description. A single word is, oh, okay, fair enough. Anyone else remember the word? Flattens out, then goes up again. It's an inflection. So the verb is to inflect. It inflects. Okay, so all you need to do really is identify that and graph accordingly. Now, the example I'm going to use is the example we had last lesson, but I'm just going to go straight into Desmos to make it a little bit faster. And you'll see there's a whole bunch of graphs I've got here, and I'm just hang on, I'll just get rid of that sidebar. Yeah, so you can see here. Oh no, you can't see the graph like an idiot. Okay, there we go. I've just got 4 factors. I've got 2x minus 1, 3 minus x plus 1, x plus 2. So this would be a power of 4 graph, right? It's a power of 4. If you just look at the x term, it'd be 2x times minus x times x times x would give you the highest power. So it's an order 4 graph. It's a power of 4 graph. And you can see there are 4 linear factors. And so we've got a roller coaster going up and then down, then up, and then down again, with the x-intercepts or the zeros being minus 2 from that one, minus 1 from that one, 3 minus x equals 0, solve it, that means x equals 3. There's that one there. And this one, 2x minus 1, will give us a 0 or an x-intercept of a half. So you can see I've got 4 x-intercepts, and those x-intercepts or zeros are each of those factors set equal to 0 and solve for x. Cuts through. All 4 cut through. They hit it and keep going. Any questions on that one? Am I going too slowly? Okay, cool. Here we go. I should have actually asked you to think about it first, so I didn't. You can see this one here is also, all of these, all 3 of these are order 4 graphs. It's power of 4 graph. So this one here has 2 linear factors, and then the third and the fourth is a double 0 here at x plus 1 all squared. So you can see that it goes up, hits minus 1 from the x plus 1 all squared, and instead of cutting through, it bounces, and then it needs to come back to this one here, which is x equals 1/2 for this 0 here. So it does that. It goes down, but then it has to come back again to cut through because it's a linear factor. The next factor is 3 minus x, which means x equals 3. Another linear factor, so it's going to cut through again. So we've got cut through, and then somewhere it goes up and down again and all the way through. Questions? How would you work out the stationary points here and here? Starts with calc and ends in your list. Hey, very good, calculus. Okay, so the only way of working out the turning points, that might be a bit of an exaggeration, but more or less, the main way one would work out the turning points is by using differential calculus. Find the derivative, set it equal to 0, solve for x, get the values, substitute into the original function, solve for y, yada, 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 all done. Obviously, this turning is a turning point we don't need to work out because it's already, we know that by, not definition, but by the way we know these things are set up. So that's okay. So you just have to work out these other 2. And the good news is we know that one is one of them. The other good news, I guess, is that in the function study part of the exam, you won't be asked to find the turning points of cubics or above, just like in 315 last year, because it requires differential calculus techniques, and that's not part of the criterion. You don't have to find them. It's fair game to be asked to find turning points of quadratics, of course. So all you have to do is estimate. If you'd gone like this and then curved it down here like that, no one's going to bat an eyelid, okay? The fact that it goes up so high, you might have a bit of a guess at, but you don't actually have to know that. Any questions on that? The reverse is not true, though. In the differential calculus unit, they may ask you to find the turning point of something. Higher than, I don't know if you remember or not, higher than a cubic? Do you remember? Don't think so. Okay, cool. Alex knows what's going on. What do you think this will look like? Just give you a moment. You can even talk to the person next to you for a second if you want to. What will this graph look like before I reveal it, roughly? It's going to, and then it's going to. We'll soon find out. Ask Naditi what she thinks. I refer you to the notes. Whoops, wrong one. Once factored, this is the behaviour. Okay, hopefully you got a firm idea in your head. I'll zoom up a little bit. By the way, you'll notice, just like I have taught my 315s last year, I always prefer to use window controls rather than the zoom in and out function using pinch zoom, because that way you can have uneven axes if you do it by hand. Whereas if you use zoom in and out, it keeps the perspective the same, which we don't always want. There we go. How's that for prediction for you? Did you get it okay or not? It's okay if you didn't. If you did, well, very well done. If you didn't, this is where you need to be. There was a cubic linear factor, and for a cubic linear factor, it inflects. So it's just 3 rules, and you're just learning it, so don't stress, but as long as you get there in the end. 3 rules. I had a linear factor, so it's going to cut through at 2x minus 1. Sorry, x equals a half there. And I have a 3 minus x all cubed, which means it's going to inflect at x equals 3. So it goes down, hits it, and keeps on going down. In terms of the gradient, the gradient is slowing down and stops, and then the gradient is speeding up again afterwards, kind of thing. So it looks a little bit like a slippery dip, doesn't it? Okay, anyone got any questions on that? I've got a couple more examples. I've got a question to ask you, but I wonder if you've got any questions. See if you can figure out what I'm about to ask you. Okay, I'm going to start the question. See if you can finish it. How do we know what Richard's thinking? How do we know that the graph goes like from here, up, through, and down, and then through again? How do we know that? E.g., I know what I'm doing, so this will make sense. If I chuck a negative there, we know that reflects the graph, right? How, ignoring that I've actually done something, but why is it that the graph wasn't actually looking like that? This also cuts through at a half, and it also inflects at 3. It's the same information, but if I was given that graph, I could always graph it the right way around. I won't accidentally reflect it because I don't know what I'm doing. What tells me that, Hamish? Say that again. Go again. I think, yep. So can I just pause you there for a second? Are you saying that a bit like for a quadratic, we look at the value of the highest power, so ax to the power of 4, because a is negative, it starts in the negative quadrant down here, and therefore it finishes here by the time we've gone through the root. Is that about right? Yeah, okay, cool. Does it that's really good. Does it work for all polynomials? certainly works for quadratics. This is called a quartic, works for a quartic. So it works for all polynomials. What do people think? Pretty reasonable, Alex? So if I change this to the power of 2, I'll have an odd power. I feel like that shouldn't have worked. Oh, yeah, thanks. Yeah. If I make that negative 2x plus 3. So if I have an odd power, the x cubed term is negative, just like it was in the cubic. I had to rearrange things a bit to make that happen. But you can see it appears up here now. So, yeah, you can sort of do one of two things. You can say if there's an odd power, then it's going to start up here if it's negative. And if it's an even power, it's going to start up here if it's negative. Or you can do what I do instead, which, because I find that a little bit confusing, I'll just return this to what it was and use what I have expressed before, which is dominant term. And the thing about dominant terms is that even if it's not a polynomial, getting used to the idea of looking at the dominant term is kind of useful. So I might just really quickly go back to Air Sketch here and talk about dominant term. So what I'm going to say, this is, I guess, for your notes. Dominant term, and like when you're actually trying to work it out, you can just call it DT. Dominant term is important to determine the start and the finish. Now, again, I'm not going to overwrite this. I will talk to it. I'm hoping it will make sense to you. Write your own notes if you're not too sure. This is being recorded and will be on Google Classroom, so you can come back and hear my explanation again. I'm just going to go through the example. I'm going to assume if the function that you've got is already in expanded form, like minus 2x to the power of 4 plus 3x cubed, blah, 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 then the dominant term is just that first term, well, the highest power of x term. That's the dominant term. If you're given a function in factored form, then you can work out the dominant term without expanding the whole thing. So that's what I'm going to do. It's a bit of a no-brainer, but sometimes, unless you're shown it, it doesn't quite click that you can do that. So I'm just using the example we've used a bunch of times. So I've got my 4 factors there, and what I do is I say, I don't want to expand the whole lot. I don't need to. I'm just looking for the dominant term. So I just multiply the x terms together. So 2x multiplied by minus x multiplied by x multiplied by x. And that would give me a dominant term of negative 2x to the power of 4. And what I tend to do is do a really rough sketch, because I think visuals are quite good for when you're trying to put all the information together. If I've got a little visual that helps me put it together without too much of a trouble. What I'm doing now is I'm kind of looking at this dominant term, minus 2 to the 2 times x to the power of 4. And I'm basically really simply saying, well, what happens when x is really big and negative, and what happens when x is really big and positive? So I look at x to the power of 4 and say, well, if I take a negative number and raise it to the power of 4, it's going to be positive, right? Anything raised to an even power is positive. So if it's negative, that means it's one of these values here, If it's negative and I raise it to the power of 4, it becomes positive, but then I have to multiply it by -2, which means the whole thing is negative again. And so I know that my graph is going to start down here in this third quadrant. Again, I'm explaining it like really laboriously because I'm trying to capture all the nuances. But in general, with a bit of practice, you're going, let's see now, that'll be positive times the negatives, negative, there, done. That's all you're doing. And even that was probably a bit too slow. With practice, you'll just look at it and go, yeah. And then I do the same thing for x being a large positive number. I've explained in a different last lesson why I'm talking about a large positive number, but effectively it's the sign that's important. If I take a positive number, which is across here, if I take a positive number, raise it to the power of 4, that'll be positive, multiplied by a negative number. Oh, that's negative again. So that means it will finish here. So it starts and finishes, or you could put an S and an S for start and finish. So a little tiny diagram there to say where it's going to start and finish, and then away you go with graphing it, knowing that it's going to go this way, then this way, then this way, whatever it happens to be. Okay. Does that make sense? Really quickly, let's just say we ended up with a dominant term of x to the power of 5, -2x to the power of 5. Then we'd be going, well, a negative to the power of 5 is going to give me a negative number. -2 times a negative number is positive. Also, it will start here. So you'd put an x there. Then you'd say, well, if I've got a positive number and I raise it to the power of 5, that'll be positive as well. Multiply it by a negative. Oh, that'll be negative. And so it'll end down here. So it'll start here and end there. So I find this way of doing it, explicitly thinking about the dominant term in terms of negative, the left-hand side of the x and the right-hand side of the x values, that's a more surefire way of getting your start and end correct, as opposed to thinking about even and odd powers. And it also works for things like, if you've got e to the power of -3x and stuff like that, dominant term works for that as well. So it works across all functions. Right, I've already overtalked it, but is that okay, guys? Alrighty, it is now almost 9 o'clock. I'm going to give you 15 minutes to work on exercise 4F, questions 2, 5. There's a reason for it being out of order and I can't remember what it is. 2, 5, 6, and then 4. So have a go at those. I know you probably won't have time to do all of those within 15 minutes, but maybe you will. And then I've got some more theory that I need to present to you at the end of this lesson.